So today we are going to study the solution of Laplace equation in spherical polar coordinates. That is solution of Laplace equation in spherical polar coordinates. Solution of Laplace equation in polar coordinates. We have discussed solution of Laplace equation in rectangular coordinates. We have also discussed the solution of Laplace equation in cylindrical coordinates. Today we are going to discuss the solution of Laplace equation in spherical polar coordinates. Okay. So the Laplace equation. There is Laplacian of u is equal to 0 in spherical polar coordinates. In spherical polar coordinates, there is r, theta, and phi. These are the spherical polar coordinates. R, theta, and phi takes the form. That is the Laplace equation when it is written in spherical polar coordinates. It takes this particular form: 1 by r square, dou by dou r square, dou u by dou r, plus 1 by r square sin theta, dou by dou theta sin theta, dou u by dou theta, plus 1 by r square sin square theta, dou 2 u by dou phi square. This is equal to 0. This is the Laplace equation written in spherical polar coordinates. Okay. Now I multiply both sides by r square so that this balances. So this implies dou by dou r square, dou u by dou r, plus 1 by sin theta, dou by dou theta sin theta, dou u by dou theta, plus 1 by sin square theta, dou u by dou phi square. This is equal to 0. Let us call this equation number 1. So this is Laplace equation in spherical polar coordinates. From this expression, we can see that here u is a function of r, theta, and phi. So here u is a function of r, theta, and phi. Therefore, by the method of separation of variables, separation of variables, u may be expressed as u, which is a function of r, theta, phi. This can be written as capital R. Here capital R is a function of small r only, capital theta, where capital theta is a function of small theta only, and capital phi. Capital phi is a function of small phi only. So where r is a function of R is a function of only R, only small r. Capital theta is a function of only small theta, and capital phi is a function of only small phi. Okay. So let us call this equation number 2. Now let us substitute equation number 2 in equation number 1. So let us write substituting equation 2 in equation 1, we get, so let us substitute u equal to r, theta, and phi. So here the partial derivative is with respect to small r, and here only capital R is a function of small r. The remaining capital theta and capital phi, they are not functions of small r. So when we differentiate with small r, we can take capital theta and capital phi outside. Okay, so I'll take capital theta and capital phi outside. So here we have capital theta, capital phi, dy dr r square d capital R by d small r. So this is the first term. Now second, here we are differentiating with respect to small theta, so we can take r and phi outside. So this is plus capital R, capital phi divided by sine theta dy d phi. Sorry, this is not phi, this is theta. This is dy d theta sine theta d capital theta by d small theta. Plus, now here the differentiation is with respect to small phi, so we can take r and theta outside. So r and capital theta divided by sine square theta, the second order derivative of capital phi with respect to small phi. This is equal to 0. Okay, so this is what we get. Now what do we do next? Next, we divide both sides by this r, theta, and phi. Okay, so dividing both sides by r, theta, and phi. Dividing both sides by capital R, capital theta, capital phi. We get this theta and phi. It will cancel out with this theta and phi. So what remains is only 1 by r. So this is 1 by capital R d by dr r square dr by d small r. Plus now this will be 1 by theta. So this will be 1 by capital theta sine small theta d by d theta of sine theta d capital theta by d small theta, plus this will be 1 by phi. So this will be 1 by capital phi sine square theta d2 capital phi by d small phi square. This is equal to 0. Okay, let me continue on a new sheet of paper. So this is what we have obtained so far. We have obtained this relation. Okay. Now we want this last term to depend only on phi. So we have a sine square theta term here hanging around. So if we want to remove this sine square theta hanging around here, what do? We multiply both sides by sine square theta so that this term will get, this particular factor will cancel out. So multiplying throughout by sine square theta, we get this term. We shall get sine square theta by r, sine square theta divided by capital R, dy dr, r square dr by d small r, plus. So if we multiply by sine square theta, we should get 1 sine theta in the numerator. So this is sine theta divided by capital theta, d by d small theta, sine theta, d capital theta by d small theta. Plus here, if I multiply by sine square theta, this will cancel out. What remains is only 1 by capital phi, d2 phi by d phi square. This is equal to 0. Okay, this is fine. Now let us take this term towards the right hand side. Let us take this third term towards the right hand side. Okay. So this means, this implies sine square theta divided by capital R, d by dr of r square dr by d small r, plus sine theta by capital theta, d by d theta, sine theta, d capital theta by d small theta. This is equal to, if I take this towards the right hand side, this will pick up a minus sign. Minus 1 by capital phi, the second order derivative of capital phi with respect to small phi. Let us call this equation number 3. Now look at equation number 3. The left hand side depends upon r and theta, while the right hand side depends upon only phi. Therefore, both sides must be equal to a constant. So here, the left hand side is a function of only small r and small theta, while the right hand side is a function of only phi, small phi. Therefore, each side must be equal. Each side must be equal to the same constant, And let us say the constant is m square. So that we'll get two equations. So we'll get two equations. That is, this left hand side equal to m square and this right hand side equal to m square. So we'll get two equations. So let us write down the first equation. So that sine square theta by r, this left hand side equal to m square, dy dr, r square dr by d small r, plus sine theta divided by capital theta, d by d theta, sine theta, d capital theta by d small theta. This should be equal to m square. Let us call this equation number 4. And this right hand side, it should also be equal to m square. That is n minus 1 by capital phi d2 capital phi by d small phi square. This is equal to m square. Or this implies that d2 capital phi by d small phi square plus, if I multiply this, we get minus m square phi, and then if I bring it towards the left, it becomes plus m square capital phi. This is equal to 0. Let us call this equation number 5. Okay. So the Laplace equation reduces to two equations, 4 and 5. Okay. Now from equation number 4, let us try to separate the theta dependent part and the r dependent part. Okay. I repeat, let us try to separate the r dependent part and the theta dependent part. So in this expression, the first term, here we have a factor sine square theta hanging around here. So if we divide both sides by sine square theta, then this first term will depend only upon r, and the second term will depend only upon theta. So let us do that. Now, dividing equation 4 by sine square theta, we get, so if I divide by sine square theta, we get 1 by capital R d by dr r square d capital R by d small r, plus if I divide by sine square theta, I should get a sine theta in the denominator. So this is 1 by capital theta sine theta. Then d by d theta sine theta d capital theta by d small theta. This is equal to m square by sine square theta. Okay, I can group these two terms together. That means this term, I bring it towards the right hand side. So let us bring this term towards the right hand side. This implies 1 by r d by dr r square dr by d small r. This is equal to, if I take this towards the right hand side, this plus will become minus. So minus 1 by capital theta sine theta d by d theta sine theta d capital theta by d small theta plus m square by sine square theta. Okay, this is fine. So I have taken this towards the right hand side. That means I have grouped the terms that depend on theta towards the right hand side, and on the left hand side, what we are left is term depending only upon r. So in this equation, the left hand side is a function of only r, while the right hand side is a function of only theta. Therefore, both of these sides should be equal to the same constant. So let me write it on a new sheet of paper. Okay. So in this equation, let me write it here. Okay. In this equation, the left hand side is a function of only small r, while the right hand side is a function of only small theta. Therefore, each side let me remove this. Therefore, each side must be equal to the same constant. And let us call the constant n into n plus 1, say. Okay, n into n plus 1, say. Therefore, this left hand side, let us equate this to n into n plus 1. So we have 1 by capital R d by dr r square d capital R by d small r. This is equal to n into n plus 1. Okay. This implies now I multiply this r towards the right. So I should have d by dr r square dr by dr equal to n into n plus 1 times capital R. Then I expand this bracket. Okay, I open this bracket. So d by dr. So d by dr operating on dr by dr first. So let us consider this r square. Let us apply the product rule. So r square, second order derivative of capital R with respect to dr square, plus. Now, next we differentiate r square and keep dr by dr. So what do we get? Twice r d capital R by d small r. Okay. Then we bring this towards the left hand side. This is minus n into n plus 1 multiplied by r. This r. This is equal to 0. Let us call this equation number 6. And we also have to equate the theta dependent part to n into n plus 1. Okay. So we should have minus 1 by capital theta sine theta d by d theta sine theta d capital theta by d small theta plus m square by sine square theta. This is equal to n into n plus 1. Okay. Now we multiply both sides by theta, this capital theta. Okay, and bring it towards the left hand side. Okay, that is fine. So we should get this implies 1 by sine theta. I repeat, we multiply both sides by minus theta and then bring it towards the left hand side. So that is 1 by sine theta d by d theta sine theta d capital theta by d small theta. Okay, then we have plus n into n plus 1 minus m square by sine square theta capital theta. This is equal to 0. Okay, let us call this equation number 7. Okay, this is fine. So what have we done so far? What we have done is we started with the Laplace equation in spherical polar coordinates. Then using the method of separation of variables, we have converted the partial differential equation into 3 ordinary differential equations. And what are the 3 ordinary differential equations? The 3 ordinary differential equations are given by equation number 5, equation number 6, and equation number 7. Okay, these are the 3 ordinary differential equations which we have obtained from the Laplace equation by using the separation of variables technique. Okay. Now let us simplify equation number 7. Okay. Before doing that, we can solve for equation number 6. The solution of equation 6. The solution of equation 6 is given by capital R. This is equal to some constant A multiplied by small r to the power n. This n, small r to the power n plus B times small r to the power minus n minus 1. Let us call this equation number 8. Then let us simplify equation number 7. In equation number 7, we put x equal to cos theta. Let us put x equal to cos theta and transform the variable small theta to the variable x. Then the derivative of capital theta with respect to small theta. This can be written as the differentiation of capital theta with respect to x, then dx by d theta. Okay, this is a chain rule. Okay, this is chain rule. We have simply applied the chain rule. Okay, this is not visible. Okay, this is fine. D capital theta by d small theta is equal to d capital theta by dx and dx by d theta. We have applied the chain rule. And x is cos theta. Therefore, dx by d theta, that is the derivative of cos theta with respect to theta. This is minus sin theta. So this is equal to minus sin theta and d capital theta by d capital theta by d small theta. Okay, so we are planning to replace the independent variable small theta by another variable x. So if we put x equal to cos theta, then d capital theta by d small theta becomes this expression. Okay, therefore equation number 7 becomes okay, this is 1 by sin theta. This, look here, sin theta, sin theta d capital theta by d small theta. I repeat, sin theta d capital theta by d small theta. This is minus sin theta d capital theta by d small theta. So this is nothing but I repeat, this is nothing but d theta minus d theta by dx. So this term can be replaced by minus d theta by dx. So let us write it like this. So we have minus 1 by sin theta d by d theta. Okay. Then we have, I repeat, this term sin square a. This is not visible. Okay. I repeat, sin square theta.
Sir,
Capital, yes, d capital theta by dx.
minus sin theta d capital theta by dx or
Sorry. That thank you. This would be dx. This would be d capital theta by dx. Thank you. So this d capital theta by d small theta. So d capital theta by d small theta. Here d capital theta by d small theta. Here we have d capital theta by d small theta. So this term should be replaced by this term, minus sine theta d capital theta by dx. So one sine theta here, another sine theta here. We should have sine square theta, and then we have a minus term here. So we should have a minus term here. So minus is here, and we have sine square theta here, and d capital theta by dx. This is okay. There I go. Plus here n into n minus 1 m square by n into n plus 1 minus m square by sine square theta. Of multiplying on capital theta, this is equal to 0. Okay, then this 1 by sine theta d by d theta, 1 by sine theta d by d theta. This d by d theta is equal to minus sine theta d by dx. So d by d theta I can replace by d by dx. Okay, so if I take sine minus sine theta towards the left, I get minus 1 by sine theta d by d theta is equal to d by dx. So this will become d by dx. So this implies d by dx, d by dx. This whole term becomes d by dx. And then sine square theta, x is cos theta. And what is the relation between cos theta and sine square theta? Sine square theta is equal to 1 minus cos square theta. That means this sine square theta, it can be replaced by 1 minus x square. Okay, sine square theta is 1 minus cos square theta. So this is 1 minus x square. 1 minus x square multiplying on d capital theta by dx. Plus, next is n into n plus 1 minus m square divided by sine square theta is again 1 minus cos square theta. So m square divided by 1 minus x square. This multiplying on theta, capital theta, is equal to 0. Okay, let us call this equation number 9. Equation number 9. And if you look closely at equation number 9, this is the associated Legendre equation. Okay, I repeat, if you look closely at equation, okay, let me simplify it further, and then we'll see that it's the associated Legendre equation. So let me simplify it again. Here again, let us apply the product rule. Let us open this bracket by applying the product rule. So first, let us differentiate this by and let us keep this term and differentiate this. So this implies 1 minus x square, the second order derivative of capital theta by dx square. Minus, now let us keep this and differentiate this. This is minus twice x d capital theta by dx. Okay, and then this term remains as it is. So plus n into n plus 1 minus n square by 1 minus x square capital theta. This is equal to 0. Okay, this this equation. Okay, so in sign 9, this is not a so let us call this equation number 9, not the earlier one, the simplified version. Okay, this is the associated Legendre equation. Okay, I repeat, this is the associated Legendre equation. Let me pause the video.